Welcome all to another session on GATE. So myself, Ardly MELBA REENA. I am an assistant professor in S.A.ENGG.COLLEGE in Department of Artificial Intelligence and Data Science. So today I am going to discuss about the topic of search in artificial intelligence. So there are two ways to do it. It is either through informed search or uninformed search. So the main difference between the informed search and the uninformed searches, the one has the knowledge of the domain or the area where we are going to resolve the problem, as the other one doesn't have the knowledge about what we are going to do it. As the figure says, it knows the knowledge about the domain. So this is the domain. So the AI knows the knowledge about the domain and how it has to progress and how it has to be evaluated. So before stepping into the informed search, let's quickly refresh the topic of searches and what are the things that has been needed for it. So when we say the search problem, states are involved in it. What are the actions and the cost that has been allocated for each and every node? What are the successor function? Successor function is nothing but this function is helpful to find out what is the next successor of that particular node, and what is the start state and what is the goal state. Start state and goal test is nothing but what is the initial start condition and what is the destination. Search tree. So finally, after we find out the solution, we get a search tree. Search tree is nothing but the nodes that represents the plan which gives the state of that path. And then the search algorithm. How are we building that search tree? So that is main important here. What algorithm are we going to choose to get the optimal solution? So this search algorithm helps us to order the fringe. Fringe is nothing but the unexplored nodes or not visited nodes. So this gives us the optimal path and it will help us to find out the least cost plan. So in informed search, the main advantage is the heuristics. We know about the domain. The domain knowledge is present there and it also gives us how it has to be evaluated. So the evaluation function has a heuristic function here, and that heuristic function is nothing but it is a function which estimates how are we going to choose it. So it is designed for a particular search problem and it is not common for all the search. So it is literally finding the path. So this is an example wherein we are going to find out the path between Arath and Busharat. So here this is the distance, the cost that has been taken to travel from one node to the another, and this is the straight line distance which is called as the heuristic function, which is helpful to reach the destination. So Arath to Busharat we will be able to take to reach is 366. The Busharat to Busharat is 0, and likewise for all other nodes it gives the heuristic value for each and every nodes. So we'll step into two types of search here, informed search. The first one is a very simple search which is a greedy search, and another search which we are going to deal is the 8-star search. So first we'll see what is a greedy search. So as the name says itself, it just finds out which is the first solution which gives. As the image says, it is having in mind that we are going to search for a diamond, but ultimately it reaches in a metal shield. So we'll see this strategy which has been followed here. So greedy search is nothing but greedy best first search, and this idea behind is to expand the first node in which has the lower estimate value, which is closest to the goal. And this implementation is similar to that of the uniform cost search, which is otherwise called as the Dijkstra algorithm, and there the GN, the evaluation function, is equal to the heuristic function. So this helps in expanding the node which appears to be the close to the goal, and it is also helpful for both the versions, graph as well as tree. It has been greedy best first search, how it has been done with an example. So our goal is to reach Busharat from Arath. So we start with Arath here. So the nodes of Arath are Sibiu, Temisala and Serith. So these three will be expanded, and among these three, CBU is the close proximity of the goal. So CBU is being selected, and the nodes that is relevant to the CBU are being expanded are Phagaris, Oradia and REENA-S. So these are the nodes which are being expanded from CBU, and after this Phagaris have the lowest proximity here. So Phagaris has been selected, and that node has been expanded, which gives the CBU and the Busharath. CBU is already the parent of the Phagaris, so that will be ignored, and Busharath is the destination where we have to reach. So the path that it is helpful for us to reach is Arath, CBU, Phagaris and Pitesti. Pitesti is another one which we will see it in the next case. So this is not an optimal one. Actually, it is not the Pitesti, it is the Bucharest. So this is not an optimal one. Why we say that this is not an optimal one is the cost that takes to travel from CBU, REENA-S.A.ENGG and Pitesti as well as to reach the Bucharest is even lesser than the path that it takes from Arath, CBU, Phagaris and Bucharest. So this is not an optimal solution, and the optimal path is the one which I have stated before. So this is the main problem with the greedy best first search. It is not giving us the ultimate solution, it gives us the close proximal solution to us. So there are two different things with the greedy best first search, which is it is not an optimal and it is not a completeness. In case if you are not able to reach to the solution in the first or two steps, then it becomes a incomplete graph which leads to an infinite loop. So these are the two things, so which says that it is not guaranteed for the best solution or a best path, and it also picks up the node with the minimum estimation, and it is not taken into the consideration what is the cost that has been required to go to that particular path. Likewise, in the incompleteness, tree-based greedy best first search is not complete as there is an infinite loop. Graph-based can be complete depending upon the completeness issue which is relevant to the DFS. So DFS is nothing but the depth first search, which is having a close proximity between it. Properties of the greedy best first search are the steps, how many steps that is being used for the worst cases. It takes O of B power D times if it is a good heuristics. If it is not, then we need some good improvement procedures for that. And the memory that is required is O of B power D because the frontier size is B power D. And is it complete? For tree it is not complete. For graph, yes, if the space is finite. And optimality, it is not. So the main problem behind this, the memory requirement is a main problem. We go in for the A star search, which is considered to be the optimal solution for the complex problems. So A star is known as the best known form of best first search, and it helps us avoids expanding the path which is already expensive by combining the two strategies, uniform cost search and greedy search. So the function, evaluation function is nothing but f of n is equal to g of n plus h of n, where g of n is nothing but the cost so far the node has taken to reach here, and h of n is the estimated cost to reach the goal from n, and f of n is the estimated total cost of the path through n to both. So the main idea here is to expand the first node which has the lowest estimated cost of the cheapest solution so that we are able to achieve this. But in the case of the greedy best first search, g of n is equal to h of n, that's why f of n is equal to h of n. But in this case, as both the values are different, we have an evaluation function of f of n is equal to g of n plus h of n. So this is a simple idea which gives us here the uniform cost order by the path is a backward cost which will be stored in the g of n, and greedy order by goal proximity will be of a forward cost which will be stored in the h of n. So this is the greedy order, and this is the uniform cost. So we will see here, it has been explained to us. So S is the starting node. S has only one successor node, which is A, and it has been calculated. You can see the G value. G value is 1 here. How does this 1 value come here is, this 1 will be taken to this condition, 1 for A, and H is 5 because the value of A is 5, so we get this. When we come to the A node, A has B, D and E. So there are 3 nodes here, so it has been expanded to B, D and E. So when we say B, the G value will be 1 plus 1, which is 2, so G is 2. H is equal to 6, which is already being given, so that is being given here. When we take the D1, the value of G will be 1 plus 3, which is 4, and H is 2, which is already been given here. Likewise, when we say the E node, the G value will be 1 plus 8, which is 9. So G is equal to 9 and H is equal to 1, so we have written here. So likewise, we will be expanding, and this A star search is ordered in the sum by G of n plus H of n. So we are just seeing this with the same example, which gives us the path from Arath to Busharath. So here, when we compare to the previous one, we didn't take the G of n value here, only the H of n value was taken into consideration. So here, G of n, the starting is 0 and H of n is 366, which is being given here. The Arath value is 366. So next, when it comes to the next one, it expands to the successor nodes, Sibiu, Temisaro and Sarith, and you can see here it has been computed here. What is the value? Sibiu is the path taken to travel is 140, and what is the value of Sibiu is 253. So that is put together, we get the 393. Likewise, the computation has been done for Temisaro, which is 447. The Sarith is 449. So compared to these 3, Sibiu is having the lowest value, so that node is being selected. And that the nodes that are being successor to Sibiu are being calculated here, is being expanded, and the value is being calculated. Among the 4 nodes, Remnich Velicia is having a lesser cost, so that node is being chosen here compared to the Fegaris. So Fegaris and Remnichi, we can see that there is a difference of 2, and this shows the lesser one. So the nodes that are being successor to Remnichi is being expanded, which says the Petisti and Sibiu as well as the Karilova is being present here. Again, we are computing the cost function here, and among this, Petisti is having the lowest value, and that node will be so expanded now. So now we come across the Bucharest, Caravio, and then the Remnichi. So we reach to the destination. So now the search stops here, and this gives us the optimal path, which is Arath, Sibiu, Remnichi, Petisti and Bucharest, which is the optimal path. So this A-star algorithm is very much effective, and it gives us the optimal path, and we are able to see 2 different heuristics here, admissible and consistent heuristics. What is this admissible heuristic is? It is optimistic. If we are not going to overestimate it, there is no chance of overestimate to reach to the goal. We see that the H of n is lesser than equal to H star of n, and that H star of n is nothing but the true cost of that node. So in no case it is not going to exceed it. And the consistent heuristic is nothing but it is monotonic. It is saying that for every successor of n dash, the n will be generated by an action with a step cost of C of n, comma a, comma n of r. So n of r is nothing but the successor of it. So this has to satisfy the function h of n is lesser than equal to C of n, comma a, comma n power r plus h of nr. So this helps us to verify the triangular inequality. So the similarities which we are able to see here, you can see the diagram. In the uninformed search, we are taking the whole direction equally to find out the path to reach to the goal. But in the case of A star search, we are mainly concentrated only to the goal, not to the other areas where it is leastly taken into consideration. So the completeness is A star is complete. It is fully complete because we have a finite step epsilon and B is also finite, and there is only finite number of nodes in the path that we have taken into consideration. So here the properties that we are seeing is there is a relative error which has been computed by epsilon is equal to definite value of h power plus minus h by h power star. So this is nothing but the effective branching factor, and the total steps that has been taken for this is O of B of epsilon power d. So if it is a good heuristics, we won't give any dramatic improvements, only slight improvements will be needed. So the memory needed is O of B power d, like the uniform cost search. So is it a complete graph? Complete search? Yes. Is it an optimal search? Yes. Like that of the greedy search, memory requirement is again the same problem with the A star search. So to summarize, A star uses both backward cost as well as the forward cost to estimate it. Likewise, A star is an optimal with an admissible heuristic. A heuristic design is a key, often use relaxed problems here. So we just see why we say that h of n is consistent, then the A star of graphs is optimal. So A star expands to the node in a non-decreasing order. It is not going to expand all the node, it just expands the node which is needed. It is not going to affect to all other things, and it is not expanding the whole graph which has been present here. So this helps us to give a contour I has all nodes with f is equal to f of I, which f of I is lesser than f of I plus 1. Likewise, cannot expand and a contour f I plus 1 until contour f I is fully expanded. Only if f of I is fully expanded, we will be able to expand the I plus 1. If the cost C star is the optimal solutions cost, then A star can also expand all the nodes which has been present within C star. So likewise, why do we have this function is, this is the result of pruning. What it says is, it is not going to unnecessarily expand the unexplored nodes, which is not at all giving any effect of it. So this is again, how do we stretch it? So the fact one is the tree search, A star expands a node in an increasing order of total F value. Fact two is for every state S, nodes that reach S optimally are expanded before the nodes that reach to a suboptimally. So result of these two factors, A star graph is always a optimal search. So this is the summarized one here. A star is an optimal if the heuristic is admissible. A star is optimal if the heuristic is consistent. So consistent implies admissibility, but admissibility does not say that it is always consistent. So it is very much helpful in solving the complex problems. So now we will discuss about few of the gate questions. This first question, it's given that consider following sentence regarding A star and informed search strategy in artificial intelligence. So the first option is A star expands all the nodes with f of n lesser than C star. A star expands no node with f of n greater than equal to C star, and then pruning is integral to A star. So as we have discussed it before, the first statement satisfies the condition, as well as pruning is also satisfies the condition. So the statement A and C are true. So which one will be correct is the B option, which says that both statements A and statement C are true. If you want to see the explanation, so A star expands all the nodes, the statement is true because A star expands the node based on the total estimated cost and it prioritizes the nodes with the lowest cost. Likewise, pruning is integral because pruning is used to avoid exploring the path which is not guaranteed to give us an optimal or a suboptimal path. So that's why pruning is a very important step. So let's go back, let's go to the second question. So second question is, which one of the following is not an informed search technique? So the first one is hill climbing, best first search, A star search and depth first search. The first three, hill climbing is also a best first search, but the answer is DFS. We discussed about the informed search, greedy best first search as well as the A star search, and hope you have learned about the informed search. Let's see in the next video. Thank you.